Consider a spinless particle of mass m. As it propagates in space and in time, it gains a momentum p on its path towards a position x. In quantum mechanics, these two observables cannot be measured simultaneously with great certainty. This measurement indeterminacy is mathematically described by this inequality, where h bar is known as the reduced Planck's constant. This inequality is widely known as the Heisenberg uncertainty principle. However, this principle does not take the existence of a minimum measurable length Lp, where p describes the order of a Planck length. Moreover, it does not account the possibility of a finite universe with a maximum length Lmax. Beyond the Heisenberg regime, and in the limit of the maximum length, the indeterminacy relation is then modified as this equation, which is also known as the extended uncertainty principle. Here, delta x is the standard deviation of the modified position, delta p is the standard deviation of the modified momentum, and alpha is a parameter where the effects of the extended uncertainty principle are manifested. The question then remains as to how the presence of a maximum length affect the dynamics of a particle in one-dimensional systems. For quantum systems, we consider the commutation relation given by this equation, where the deformed phase space operators are then given by these two equations. The operators in lowercase are the undeformed ones, described by the usual quantum mechanics. Now, for the classical dynamics counterpart, we convert the commutation relation to the classical equations of motion using a deformed Poisson bracket given by this equation. This is also formulated in terms of differentials as this one. Here, the lowercase variables are the canonical variables. The implications of these deformed equations are the focus of my thesis entitled Modifications of One-Dimensional Quantum and Classical Systems due to the Extended Uncertainty Principle. This has been Marpenser, and thank you very much for listening.